This next lesson is on data storage, and we're going to look at several things. We're going to first of all look at data as a resource, as it's very important, and it's actually surprising how many people, and particularly organisations, don't really appreciate this. We're going to look at relational databases, NoSQL databases, and a little bit on big data, so to compare the three different forms of data storage that we're going to be using. So, data as a resource. A lot of people don't understand really what they've got in terms of data, and we're going to have a look at some of the issues concerned. So, data is everywhere. The planet is producing ridiculous quantities of data, and every business activity basically requires or produces data, but a lot of it goes unused or unnoticed, and it may not be obvious what's in the data that's useful. So something that's in a database or in a library or a repository is clearly data, but what about other things? Log files can often contain very useful information. Emails, that's always an issue, isn't it? You get these huge email chains where people send emails backwards and forwards, and I find it's very hard to find the information in them. It gets buried in the chain. Instant messaging. A lot of useful stuff is actually exchanged using IM systems. A lot of people use it all the time when at work, chatting away about various things, and that information may not be captured. And so the thing is, a lot of companies are starting to realise, well, actually, we've got all this useful information lying around. We're not using it, but we might be able to do something with it. So ask the question, what do I have? So obviously, if it's stored somewhere, it's obvious. What else is there? Is there anything interesting in the log files, for example? What information is being captured or not being captured by the organisation? What data's being produced and used? What's being thrown away? Can it be used somewhere else? So there's lots of things that we need to ask the questions for, and that leads to some interesting possibilities. Data, where is it? Where's it come from? Is the first question. And then you've got to get it in the right place and in the right form at the right time to make any use of it. And is the information easy to extract? If it's buried in the middle of a log file, you might have to do some fairly complex textpilation to get the information out of it. Here is an example of a case study. It is actually based on a true situation with a friend of mine. This friend of mine is a very, very good astrophotographer. He's done some amazing images of the sky. Things like he did a picture of Orion, a photograph of Orion, which was something like 400 photographs all stitched together to make a massive image. But then I started talking to him, and I thought, well, actually, you've got a huge amount of raw data there, and it's taken over a period of 4 years. There must be something useful in there. If something moves, changes, or appears, we might discover something interesting. And we've actually started a process of trying to extract that information, trying to see if there's anything there that looks interesting. This is also based on a true story. We've got a large retail company, and it keeps its transaction data from all of its checkouts. So basically you can tell what was bought, where and when, and even down to which checkout was used. Now, there could be some very useful information in that data. So let's just have a think about it, looking at some particular stories and see what patterns we can find. That's what we're looking for, is patterns in the data. So we've got an example. It's a supermarket, it sells sandwiches. The supermarkets in the city centre show a peak of sandwich sales at certain times of the day, in the morning, lunchtime. So it's fairly obvious that people are buying their lunch either before work or at lunchtime, which is fairly obvious. And so what happens is the store can make sure that they've got a plentiful supply before the peak starts. So you make sure there's a delivery at, say, 7 a.m. and at 11 a.m. to make sure that there's plenty of them there so that they give plenty of choice and get a bit of sales. And another one is if you think about the demographics. Now this is quite complex as there's many possibilities. So you think about the products. Some are gender specific, some are age specific. Some people would tend to buy younger people would tend to buy certain products, older people other products. And also the basic or premium products. Which one do people go for? Do they pay a bit more for top rate food or something? That should indicate something about their demographic in terms of earning level. And maybe the quantity, you can get some idea of how many people are in the household, and maybe what type mix you got, whether it's young children or they're all adults. So by looking at the demographics and seeing if a particular type of individual falling into various categories favour a particular store, you can actually increase the product range that favours that particular demographic so that you will increase the sales. Quite a good idea, maybe not so obvious. Another one, if the position of the checkout, some people prefer a particular checkout. So it may be based on some things like, first of all, the technology. If you used to have the automatic checkouts, some people don't like to use them. They prefer to deal with a real person. Some people prefer to pay cash rather than by the smart payments mechanisms we've got now. Maybe the location. So, for example, some people buy, say younger people buy certain products, checkouts near the exit and pay by phone because they want to get there in and out quickly. So you can put things that they're likely to want to buy close to the doors and make it easy to use. And make the checkouts that use the, say, mobile phone for payment available in the locations where the people like to use them. Again, make use of the data to increase sales. So big business opportunities there based on this very simple idea, but quite difficult to extract information. It's a useful resource. This data was being thrown away, and the particular organisation decided they wanted to do something about it. And so by looking at the demographics, you can determine various things, like when people buy things, what they buy, what checkouts. So you can basically improve your layout of stores and basically on the location of the stores. You can change your product range to suit the demographics, make sure things are fully stocked at peak times, and make sure you've got the right checkouts and the right number of the checkouts of the different type. That's the idea. So data is a resource. Now, I've heard that story being told quite a long time ago. Data is a resource. And people still not really doing an awful lot about it. So how do you deal with it? We can always add more hardware if we need more power. And you've got things like internet applications that have vulnerabilities which can cause issues of scalability. The other thing is data is constantly evolving. So, for example, in a database, if you have a very efficient database working top performance, and then you merge in some new data, say you have a merger with another company, the data can suddenly become very badly organized, and the database can become very inefficient because of the changing demographics. So that's one thing that we can think about. And there's also data recovery. If you've got databases, you can recover the whole database, but can you recover just a part of it? It's not so easy to do. And recovering a whole database can mean the information is lost. And of course the volumes. I was talking to a DBA at a bank who told me that over the last couple of years the database size had risen by a factor of about 1,000, which is quite staggering, the amount of information that's been added to the organisation. And also it's hard to find people that are good at managing data. So think about the organisation. You've probably got companies that got large numbers of databases. Does every single application have its own database? That quite often is the case. And that means that the servers are probably running at fairly low capacity. And so you may be able to do something about that, make use of things. There's also regulation requires extensive auditing, which is getting increasingly difficult, and it has performance overhead. And we've got the situation which is rather bizarre that in the financial sector, database administrators are not allowed to do their job because they're not allowed by the regulators to access production databases, which is rather surprising. And also as the volumes increase, the security issues increase, and you have to think about how to improve the security and what level of the security you want. The internet this is one of my pet subjects. The internet's got over 1 billion websites and 4.7 billion web pages. That's rather a big number, isn't it? And these keep changing, of course, as sites appear and disappear. And a lot of it is actually archived. The Internet Archive does try and capture as much as possible so that information is not lost. But what happens is, of course, that as the internet grows and more data gets added, the actual signal-to-noise ratio starts to drop. I don't know if you've noticed that if you try and do a Google search for a particular thing, if you do a Google search for, say, a celebrity, information about a celebrity, you'll probably get lots of hits and it's reliable information. If you try and do an internet search for something like how to write a particular application in computer software or some details of some very exotic physics or something like that, I think you'll find it's very hard to find any information whatsoever. So, for example, I wanted to find the definitive information about how to calculate the position of the planets in the solar system. It took me 18 months to find it. It was very, very obscurely placed. And even now, I have to remember how to get the search right to get to the right place. And also, there is a lot of information which is just simply not there. Again, there's another project, which is the one I mentioned earlier about the astrophotography. There is no definitive catalogue that names all the stars. There are a lot of different catalogues, each using a different name. So if you take a particular star, which is one I'm quite fond of, which is Rigel in Orion, it has all of those different names depending on which catalogue you use to look it up, which gets very confusing. Is Rigel Beta Ori? It's a very odd set of notations, and there's no single catalogue. The other thing is that we have the Web Consortium W3, they define the standards for the web, but people don't have to follow them. There's no regulation that says you must do this. And a typical point is the web browser. Web browsers typically display content differently, and some web browsers don't display content at all. So trying to make an application work and display well on a range of web browsers is actually very difficult and very time-consuming. And there are some surprises. Internet Explorer is notorious for not following the rules. But even then, I found a recent one with Google Chrome that I wanted to put some equations into a web page. I used the MathML markup language only to find that Google Chrome has discontinued support for it because they haven't got any people to do it. It's also hard to find out how to use tools and libraries. I've been doing some work on Spring and Hibernate recently for Java and find that the documentation is usually out of date. And you try and use it, it simply doesn't work. And then you have to try and find out why it doesn't work and what the change was to, the API to make it up to date. There are certain sites, such as Socratic and Quora, who strive to get good quality answers to questions to support people, particularly in the sciences. But they are fairly rare, and they have trusted users who police the site, which is extremely good. And very good answers are flagged as exceptional, which helps. And if somebody posts something inappropriate, they delete it. So relational databases, I'm sure you've all encountered relational databases. It's the traditional storage which has been around for quite a long time, and it's amazing how badly utilised many of them are. So we want to look at some issues, and we're looking at it from the perspective of improving the performance so we're getting better applications. The model for relational databases has been around since the 1970s, so it's quite an old technology. We just have data organised into tables. Every table is a set of objects of some kind, or part of objects. We have the attributes, columns, and the rows of the object. So I think of it as a kind of object model where, yes, a row in a table is an actual object, column is an attribute of an object, table represents the family of objects. And we have uniquely identified rows which use keys which identify the columns which are unique to make a row uniquely identifiable. Now, this is the first thing that's interesting. The order in which rows are stored in a database is technically not defined. In practice, if you do a select star from table, you'll probably get the data out in the same order in which you inserted it. But that's not actually guaranteed because it depends on how the data is actually physically stored by the database itself. It's often the case, but not always, and a lot of people assume it. Put the data in a particular order, assuming it comes out, but technically, according to SQL, it's not supposed to be ordered at all. And we have to have normalization as well to get rid of some rather nasty inconsistencies which lead to data being corrupted or incomplete or something. Normalization is a way of adjusting the tables in a database to make sure that there are no inconsistencies. There are different types of normal form. Some of the most popular ones are first normal form, second normal form, and third normal form. Third normal form is difficult to understand and many people get it wrong. There is in fact a fourth and a fifth normal form, each of which is stronger than the other. So first normal form is relatively easy to implement. It gets harder to implement second and third normal form. The consequences of over-normalizing is that the database is very difficult to access because you have to do a lot of table joins. The advantage is you don't get any problems associated with duplicated data which doesn't get updated completely, and inconsistent data. So the whole purpose of normalization is to make sure that the data in the database is completely independent, no duplications, no inconsistencies, and so you can guarantee that data integrity is maintained. The first normal form is the story is that the table has to satisfy certain conditions. The basic idea is that there's no repeated groups or two columns that have the same information in it of a different type or different value. So if a table is the first normal form, if it follows the conditions there. So there's no ordering of the rows, which is fairly, well, that was what we said before. There's no top to bottom ordering of the rows. There's no ordering of the columns. It doesn't matter what order the rows or columns appear in for it to operate. There's no duplication, no duplicate rows. That is usually enforced by the keys, but not necessarily. If you don't have keys on the database, which is sometimes the case, you may have a duplicate rows. And it also says don't have anything hidden, such as like comma-separated lists for columns, that sort of thing. That makes it normal. And then we have this wonderful phrase about every row and column intersection contains exactly one value of the appropriate domain. What does that mean? Well, basically we don't have two phone numbers. Okay, that's the reason. And if we've got this particular table there, we've got phone 1, phone 2. That is what makes it non-first normal form, because effectively phone 1 and phone 2 contain the same type of information from the same domain. And so it's not the right way to do things, having phone 1, phone 2, because if you add a phone 3, that causes a few problems. And if you don't have a phone 2, you've got a null to deal with, which is also problematic. So to make this database first normal form, what we need to do is extract out the phone numbers into a separate table, and then we just have a key, which is the customer number, which enables you to link the two tables together to reconstruct the original unnormalized information in its entirety. The terminology is wonderful for these things. So a table is in second normal form if it follows these following rules. First of all, it's got to be in first normal form, obey all those rules. And then we have this wonderful descriptions of saying what table is supposed to be. So basically what it says is that if you've got a composite key, then every column should be dependent on all of it, not just part of it. So that means you don't have something that's only dependent on part of the key. So, for example, this table is in first normal form. Everything's fine there, but there is a problem that we've got the loan number and loan amount. The loan amount is dependent on the loan number, but it's not actually dependent on the customer number. Okay, there's a dependency between the loan number and the customer number, but that is a partial dependency, which makes it non-to normal form. So what we do is we take out the loan num and the loan balance, which is the partial dependency, into a separate table. Obviously the first table index is the second one. You join the two to reconstruct the original first normal form data. Right, this is the tricky one, third normal form. There are others as well, 4 and 5, but we normally stop at this one. It's a tricky one because a lot of people don't get it quite right. And there's a misquote there of Ted Codd, who's the guy that defined it, which based on a phrase that it's the idea is that everything is dependent on the primary key and nothing else. So that means that if you've got two columns and one is dependent on the other, but they're not both dependent on the key, then it's not in the right form. It's not third normal form. So let's have a look at an example. So here we've got a two normal form database. It's based on the Wimbledon results. So we've got year, winner, and nationality. Well, if you look at that two normal form, it's not third normal form because the nationality is not dependent on the key, which is the year. Okay. So what we need to do to make it third normal form is split that out. So we've got the year and the winner, which is fine, and then second table is the player's nationality, and that gets rid of that duplication, and also it gets rid of that partial dependency, which that transient dependency which we had before. So, primary key. A table in a database doesn't have to have a primary key. They often do, but it's not necessary, and some actual database tables can't really have a primary key because there's no real candidate for it, or it doesn't work too well. So basically, all the primary key is one or more columns that uniquely identifies each row of data. It can be more than one column, say it's a composite key, and if it's a naturally occurring piece of information that's in the data, it's called a natural key, as the name suggests. We often use a number. It's called a surrogate or synthetic key. We just add another column which has got a unique number which we just generate from the previous value, and that value is then the primary key value. It does make it more difficult to use as a person, because you've got to generate or find the surrogate key, as there's no naturally occurring thing associated with it. So which number is associated with which data, there's no real easy association there. Also, a foreign key is basically a column in a table which stores the primary key value of another table used to join the tables together, showing the relationship there as an entity relation diagram. Well, I mentioned that tables about being a set. In set theory, a set is an unordered list of unique objects in the mathematical sense. If a database has a primary key, we know every row is unique. So therefore, it's a set. And because technically a database is unordered, then it follows the rule of set theory. It's an unordered list of unique objects. When you query a database, you also generate a set. It's basically a table in memory, the result set. Thinking of databases in terms of sets helps an awful lot in getting the queries to work. Think about the operations that you can perform on sets and get the results you require. If you think about the set operations, you can map them directly onto database operations. So the normal join you do is you're finding the intersection of two tables or two sets, which is the inner join, and that shows the intersection there. There's a full outer join or Cartesian join, which very few people actually use because it generates massive amounts of information, where you associate every row of one table with every row of the other table. So you get the combined number of rows in each table multiplied together as the result set. Then we get the left and right outer join, and there are set operations. Basically, the idea is we want every row from one table and associated with the corresponding row in the other table if it exists, or nulls if it doesn't exist. So it's a fairly common one. The difference between a left outer join and a right outer join is just which table you specify first. I tend to just use left outer joins actually, because all I've got to do is change the order of the tables, turn a right outer join into a left outer join. Although using the smallest table first often helps. A full outer join like a Cartesian product the answer is yes. Basically, if you've got like 3 rows in one table and 4 rows in the other table, you basically get 12 results. Every row of the first table associated with every row of the second table. So yes, it's a Cartesian product. It's often called a Cartesian join, something you don't do very often actually, because it just generates massive amounts of information. The inner and outer joins are the most common, as the most useful. We have another issue with standards. We mentioned that the internet's got problems with standardization. In particular, that the W3 consortium puts the rules together about what HTML looks like, and the vendors of the browsers may choose not to take any notice of it. In the database world, we've got the structured query language, SQL. Now, SQL has been a standard, but actually Oracle as a database predates it, and all the database vendors tend to add extensions to the SQL language for doing various things. So this means that certain constructs are basically bulk standard SQL, which is fine, but certain other operations, like if you want to have stored procedures, if you want to do certain administration tasks, each of the database vendors will have their own syntax and command set for doing that, which is effectively part of SQL, but it's non-ANSI, non-standardized. So, for example, Oracle has got various things like bulk collects and for all, which are operations for doing bulk data processing, incredibly efficient if you use those rather than do things any other way. And there's also things like scalar functions. You've got your sort of count and max and min, but there's all sorts of other ones. Oracle has got a very, very large number of functions, some of which are rather exotic and you don't use very often. The syntax of them can be quite interesting, to say the least, because they have some very odd ways of doing the processing. You can't really avoid it. If you want to do something reasonably efficient in a database, you almost certainly need to use the inbuilt functions. They might also suit your application better. Now the thing is, if you don't use the non-standard features, you can do that. And people would argue maybe, well, we should use the standard features only because we might want to port it. I think it's incredibly rare that an organization will change database vendors, because the risk and cost of doing that is huge. Okay, there might be issues there. A company merges with another one and they're both using different databases. They might want to try and get a standard across the organization, but that's a pretty major undertaking and won't be done very often. And the thing is, if you've got, say, an Oracle database, you'll be paying Oracle quite a lot of money for the connections. You may as well make use of all the features of the database and make it very, very efficient. Although there is an issue, which is, where do you do the processing? Do you put business logic in the database, or do you do it in the application code? The whole story is very, very controversial. Some people actually say you must never put business logic in the database. Others say that you may as well make use of it and put the business logic down there in the database in terms of store procedures. But you've paid for the database, so you may as well make use of the features in it. You can do some really clever things. It's amazing how many applications do the following. They read a lot of data out the database, they do some processing, and then they put it back in again. That requires quite a lot of I/O. It's quite inefficient, where in fact if you did it directly in the database itself, you can do it much faster. So I actually worked on an application where a series of database operations which are actually written in COBOL. It took about 4 hours to run every day. I replaced the COBOL, which was one of my greatest achievements, getting rid of COBOL, with stored procedures, and it ran in about 20 minutes, quite significantly faster as a result. Now, indexes are another subject which is quite controversial. And what is an index? It's basically a data structure which enables you to access the data in a particular way which is more efficient. The consequences of non-indexing is that you have to do a thing called a full table scan, which is you literally have to go and check every single row of the data in a table until you find it, which might take a long time. The index is a data structure which gets you there quickly by some kind of hashing or some other algorithm that's used. Now, if you have an index or not, doesn't change your SQL. The SQL is completely independent of the index. What it will do is it changes the way that the database will execute things. So when the database tries to decide how to do the execution of the query, it will look at the indexes and decide whether or not to use them. And indexes are also in different pieces of storage typically from the data in the table. Whether there's an index on the data on the table or not doesn't affect the data itself. We've got indexes which can be unique or non-unique. And the primary key of a table is always associated with an index, which has caught me out in the past. I was working on Oracle. I wanted to get rid of the primary key constraint. So I deleted the primary key constraint and still couldn't do what I wanted to do because I hadn't deleted the index associated with the primary key. Because when you add a primary key to an Oracle database, it will create an index as well if there isn't one already there. And the diagram shows how things are organized in that you can look at part of the data and it'll take you to another table which will show you where the actual data is stored. Now, one thing that crops up a lot is a lot of databases in the real world. They've got a lot of indexes and they're often not used. And the problem is that if you have an index, all indexes take up a lot of space because effectively you have to replicate the data in the columns that the index is applied to. They also slow down operations such as insert and update because when you insert a row into the table or update a row, you probably have to change the index as well. And most indexes are never actually used because the actual database engine itself may choose not to use the index. You can't really force it. And quite often the case is that the index is sitting there and the database chooses not to use it. The optimizer decides it's not going to use it. So a few rules and guidelines for indexes. Columns which are fairly unique in value. If you've got a table where a lot of the column values are the same, it doesn't make much sense to add an index because it's not going to help an awful lot. And also queries that return small amounts of data. There's a guideline of 15% of the rows. If it returns more than that, it almost certainly isn't worth having an index. And contrary to popular opinion, a full table scan is not necessarily a bad thing. For some database operations, a full table scan is the way forward, and it's the best way of doing it. So don't put indexes on columns that change a lot because of the insertion and update problem. Don't put it on a small table because you don't need it, because you've got a full scan of a small table is going to be fairly quick. adding an index is just going to add overheads. And a lot of columns with lots of duplicate values don't make any sense, because the index is looking for things that are fairly unique, not things where a lot of things are the same. And one thing you can do is you can ask the database for an execution plan for the various SQL statements. The execution plan that the database gives you may not be what it actually does. That's the worry. That you can say, how are you going to execute this query? It'll come up with a solution which it may choose not to do at the time when you actually do the query. Though there are ways you can say, okay, what did you actually do when you execute this query, and find out whether it used the index or not. The question about the table scan causes performance issues. It is very expensive if it's a very big table. But if it's a small table, and or the data in the table is fairly non-unique, it doesn't make any difference, because it's going to have to do a full table scan anyway, effectively. A very popular, if you've got an index on somebody's surname and you take a very popular surname which many people have that share, then indexing that column is not going to make any difference. So table scans are not necessarily a bad thing. Yes, they're going to involve CPU usage, but it may just be that the database chooses to do so anyway, and you can't stop it from doing a full scan. Another thing is the tablespace. Tablespace is a partition of the database's storage. So database storage is typically broken up into a number of tablespaces. A tablespace can contain any of the artifacts in the database. So the tablespace can contain any of the objects, tables, indexes, anything else, synonyms, any of the other pieces that live in the database. And a tablespace is a set of data files, and there are sort of guidelines as to when to use them. Some DBAs put tables in a different tablespace to their indexes for performance reasons, in that when you're scanning the data file for the table and for the index, if it's on the same physical disk, you could get the heads on the disk moving a lot, jumping backwards and forwards between the table and the index areas on the file system. And I worked in one organization where it was required that the table and the index went in a separate tablespace. In fact, in today's world, that argument about the head-seeking operations doesn't really apply, because most databases are stored in data centers. The actual storage is going to be some network storage device, and you've got absolutely no control over which physical device the actual table spaces are stored on. So it may make no effect whatsoever because of the way we use our technology these days. And of course, there's one of the biggest problems you get with some databases is there's a special table space in Oracle called the undo one. So when you do certain operations which need to be committed, it puts the intermediate steps into the undo space, and I've often had problems where I can't do an operation because there's enough space in the undo space to take the operation. And you have to do some very interesting things to make that work, which often requires removing indexes and putting them back on again, or rather switching indexes off, doing something and then switch them back on again. Now this is really neat. When I first saw it I thought, oh, this is curious, and then I started looking into a bit more detail, and it actually makes an awful lot of sense, and it's called petitioning. We have the problem, we talked about table scans, and if you've got very, very big database tables, which is very common these days, you're going to end up with millions of records or rows in each of the tables. Now, if you think about the data, what is the nature of the data in the table? So, for example, you might find that some of the data is quite old, and you'll very rarely, if ever, access it. You might do it for auditing purposes, but you're not going to be doing anything serious to it. Other data, which is probably the current data, the most latest additions, is going to get changed quite a lot. So effectively, you've got parts of the table which are going to be accessed very frequently, and parts of the table are not going to be accessed much at all. So what we can do is use a petitioning mechanism, and what that does is you basically split the table based on some query or partial query or condition, and physically store the parts of the table in different places. So effectively, when the database does a query, it'll only access the piece of the database table that you actually want to use, and will not use the rest of it. And it means you can have the petitions can be in different table spaces, different storage, and the SQL doesn't change because the query still works. It's just that when you build the database table, you add the extensions for petitioning, which make it work quite well. So that's really quite a neat way of doing it. And as the diagram shows, you might say want to break your table into pieces based on time, like months. And so the latest stuff is in one place, the other stuff is just left if you want it. Petition, logical or physical, it's a bit of both because you actually physically store the different petition pieces. So a table petitioned into, say, 4 petitions, each can be on separate physical devices, but when you do the queries, the nature of the petition, the condition that decides which petition you're using, will dictate which piece of the data is actually accessed by that query, but it doesn't affect the query itself. So when do you do this? Guidelines. When it's bigger than 2 gigabytes. It's one of the rules. If it contains historic data which is read-only, or effectively read-only, you don't do it very often, that's a good candidate. Put that old data into one or more separate petitions, and so that you don't access them unless you absolutely need that data. And then there's also, if you want to spread the table over multiple storage devices for various reasons, like size reasons. There's another suggestion that indexes should be petitioned, and that is when you change the data, say you delete something, if you delete data or update the primary key or insert something, the indexes may need to get recreated or rebuilt. If you petition the indexes, then it'll only update the section of the index which is affected by the change in the data. It is incredibly powerful. It is now seen to be the way forward. Let's say a few years ago I hadn't really heard of it, but now it's very much the flavour of the month. And put, say, frequently updated data into several small petitions, old data into others, and it'll only scan the petitions which need to be scanned. So there's different types petition. The list petitions, you take a particular key and specify a range of values for that particular key. So you could say if you've got your organization works in, say, 3 regions, the key that defines the region, you can use a petition to say, right, I want the East States region to be in one petition, the West States in another, and Central in another. And so that means that when you do operations on any region, the data for the other regions will not be looked at in any way. The range ones, usually for dates, you basically say, right, this petition is for this period of time or for these particular range of values of something, which is very popular. I think range petitions are quite the commonest ones. And then the other one is a hash petition. It's when you want to petition, but you don't really know how to do it because there's no obvious range of values or particular values that can be identified which break the data up. This basically says to the database, you get on with it. I want you to use petitions. I want you to use so many petitions. I don't care where the data goes. And so what it does is it'll use a hashing algorithm of some kind, which will decide which rows go into which petitions. And so it gives you a kind of load balancing between the different positions there. But again, you've got the same thing that when you do a particular operation, the query only affects the data in the petition that's being used and nowhere else. How should we agree on petition keys? It's normally you choose the key based on something in the data. So for example, the obvious one is date. If you've got a timestamp or a transaction date in the database, then you can say, right, everything that's more than, say, 2 months old is effectively archived data, and so we can put that into a separate petition to the live stuff. Otherwise, it might say it could be done regionally, as we saw in the other example that specified that data for each particular region we operate in goes into separate petitions. You can tell basically on the looking at the data, you have to understand your data is the most important thing. It's a very important thing to be able to do. Understand what the data looks like and which pieces are being used more frequently than others or which ones should be kept away from others, and choose your key usually based on that. And it's usually like a date field or a region field or something, maybe a product line key or something like that. So it's no hard and fast rules, and if you don't have an answer, use the hash and then let the database choose for you. Yes, petitions are definitely based on the use case. Each one will have its own petitioning rules which you would decide on. So I've touched on this before. Where do you do the data processing? Do you use stored procedures? Do you use just put your SQL in the code? I prefer to use stored procedures for several reasons. The first one is I don't like to see SQL statements in the actual application code. So yeah, I don't like SQL in the code. So I don't like to see Java and SQL in the same file. It's actually cheaper in many ways to call a stored procedure because you don't have to do any processing in the database, and you split up the logic so in a way that you say, okay, moving data around is best done in the database because it's faster, rather than dragging things across the network. And so some people say don't use business logic in the database because it puts it in a different place. But if you think about the three-tier model of the people have, think of it like a fourth-tier model where you've got your business layer and you've got like an extension of the business layer, which is a middle tier which inside the database which is where the PLSQL or stored procedure is stored, and then you've got the actual database behind that. Well, there's a number of tools you can use for database deployment. Yes, there's the Oracle Data Integrator. There are others which are basically used for storing database information or being able to specify what the changes to a database look like. There's quite a few tools around that can do those sort of things. Okay, so this is controversial. I did one program on databases and there was nearly a fight broke out between two sides of the room because one said it's got to be in the application, the other said it's got to be in the database, and neither would agree to disagree. So if you're transforming data, reading from one set of tables and writing to another set of tables, doing transformations, databases are very good at it. And in particular, you've got the bulk operations, which are very, very efficient. So you do a bulk collect and then a bulk write. And so make the best use of your database. Try not to drag stuff over the network only to put it back again. Think about doing aggregations and some things inside the database. If you're doing processing, which for displaying results, stick those in the application code. There's no hard and fast rule here. It depends on use case again, which one to use. Now, this is a good one. Dynamic queries. Often you can't formulate the SQL statement at compile time. You have to actually assemble the statement at runtime. This is fairly common, particularly if you're trying to say do a query based on, say, demographics, which are selected by a user interface, and you don't know which combination of columns you're going to use for any particular query. And so you need to build the query up. But you have to be careful. If you do string concatenation to build an SQL query, you're asking for an SQL injection attack, which is SQL injection is probably one of the biggest causes of problems associated with databases. And it's amazing how many people do it. You tell them, do not do string concatenation. The next thing you see, string concatenation is in their SQL, and we have a potential problem. So this example code here, we're passing in a customer ID as a string, and say that comes from a form on a web page or some other source of information which is user controlled. If we replace the actually call that update customer procedure with that code in there, what it does is the quote one just terminates the open quote and adds the one to it. The semicolon starts a new statement, and then we add a drop table, and it does. So what happens if you execute that particular statement there? It will cause the table to it'll do the update, and then it'll immediately drop the table and commit it, because the drop does an implicit commit, which is even worse. So things to do. First of all, make sure that you use bind variables. So you don't use string concatenation. The bind variables are basically where the SQL is wrapped up and inserted into the statement by something else. It might be a prepared statement in Java, or it might be use a bind variable in the database itself. So try and avoid the string concatenation. Use bind variables. You can't always do it because you might need to add complex, say, where clauses, which can't be done without it. Give the database user just enough permission. That was the security thing. So to give people the minimum access they need to do the job. It's amazing how many databases out there in the real world are accessed by people and programs using the schema owner of the database. That is just wrong, because the schema owner, as the name suggests, can do anything they like to the database. If you only need to be able to read the database, make sure they don't have write permission, then you can't have a problem. But there's also things, and there are bits of software out there that will do it. Check the input parameters to look for things that are harmful. Very long strings, punctuation characters, which are punctuation of the SQL statements, and the dangerous keywords in SQL, which tend to do things like delete or remove or change data. And try and test your procedures. Make sure that you can try and break it with a potential injection and see if you can avoid it. And now we get to another aspect of databases. Again, this is an interesting one. Object relational mapping, because if depending on your perspective, you might think it's a good thing or a bad thing, and in the DevOps environment, we have to deal with it from both angles, which is more interesting. So what happens is you've got objects. Object graphs is just a fancy term for a collection of objects all linked together, or that's typically an object model which is live, where you've got all your objects and they're contained and using objects. And we need to persist the objects, all of the objects, into a database. So first of all, we're going to map the objects onto tables, and then we're going to have to query the tables. The object relational mapping software does that mapping and generates the SQL, so you don't need to know the SQL. You just work with the mapping and it'll just do everything for you. It's got things like lazy loading, which is where if you've got one object which has got child objects, it won't load the child objects until you try and access them. Cascade, if you've got a composite object, if you delete it, it'll delete all the component parts. And we've got caching as well, where you don't have to hit the database with queries over and over again, you just store it. What the ORMs do behind the scenes can be quite interesting. So where the thing works with the different perspectives, from a developer's perspective, it's very easy to use an ORM, particularly for new applications. You just write your code, you annotate the persistent objects, and the ORM does nearly everything for you. From the operations perspective, it's a slightly different matter, because you've got very little control on what the ORM actually does to the database. So how often does it query it? How often does it do updates? Does it do bulk operations and things like that? And it is often the case, particularly if things are not configured quite right, that the ORM will cause a lot of performance issues because it keeps hitting the database with multiple requests, which it could have simplified in some way if it was not configured correctly. The object relational mapping provides APIs, yes. It's done in various forms. If you use something like Hibernate, which is one I've been using recently, you annotate your Java objects to say which classes and which attributes of the classes are persisted and what table and what columns they put there. They also provide various APIs for controlling the operation of the ORM. And they also provide a query language which is not quite SQL, it's based on objects. So they're fairly sophisticated things. So yeah, if you get something like Hibernate, it's got a vast quantity of APIs as well for doing all sorts of things. Because for example, if you've got a data type that doesn't naturally map to a particular column or columns in the database, you can specify how it's done by writing code that uses the APIs to tell the ORM how to do it. A good question, why should we use ORMs? It's basically, the reason is that mapping objects onto database tables requires a lot of plumbing to make it happen. So for example, if you use the standard sort of database API, say like in the Java world, if you use JDBC, if you want to persist an object, what you're going to have to do is for every operation, you're going to have to generate the SQL for that operation and populate the SQL statement with the actual values from the object that you want to persist. That requires quite a lot of code. Now, if you use an ORM, what you do is you do a simple annotation of the object. You set up a configuration and make a few API calls, and it's all done for you in a matter of seconds. Particularly if it's partially set up already. And so, for the developer's perspective, ORMs are great. They're fantastic. They simplify the amount of coding they need to do, and they can concentrate on the thing that makes the money, which are the business objects. So developers like them in general, although some things are not so easy to do. Sometimes relationships between objects can be quite tricky to get right. Say operations guys sometimes don't like them because they have performance issues and impacts which they have to deal with. Right, so that's the ORMs. There are a number of them around. In the Java world, there's things like Hibernate and Ibatis, and there's the Java persistence APIs, and there are several of them. Spring JDBC, there's a choice of things that are out there. They're all slightly different, but they do the same job. You provide a mapping between an object and the tables, which is usually done either in XML or annotation forms, and then it just works very simply out of the box. With this, you have completed the concept of relational databases. Now Randy will explain to you the steps involved in creating and using a relational database through a demo.
Welcome to DevOps Lesson 3, Lab Number 1. Let's go over to our terminal, and the first thing we want to do is clone a repository with the source code that we need for the labs for Lesson 3. So we're going to go up to GitHub, github.com, and the area is Simplilearn, DevOps. Specifically, the repository is DevOps Lesson 3. Pull that down. Good, we're done. Now we're going to go into that directory and notice that there are the 3 labs already set up for us. So we're going to go into lab 3.1 and go into, well, let's take a look at what we got. There's a subdirectory called testdb that contains information that we're going to want to load into MySQL. And notice that it's all GZ files. They're compressed. So we need to use the GNU unzip program. And we want to specify any file that ends in GZ. And let's try that again, because I misspelled it. Takes a moment, and let's take a look. Now we see that we have all these dump files, which is great. So let's go up a level, and we need to take these scripts and turn them into executables with a chmod directive. We'll just set everything to make it easy. And there they are now executable. Now what we want to do is create a Docker volume. So a volume is a container whose function is to retain state. And we're going to create that on our own computer, and we're going to call it MySQL _ data. So that's created, and we can take a look, volume ls, and there it is. That's our volume that was created. Okay, so now we need MySQL. So docker pull MySQL, we want version 5.7, and we'll see that it comes down in layers pretty quickly. So let's see how big it is. Docker images, and it's 400 megabytes. Okay, that's just fine. Now let's take a look at some of these scripts. So there's one called run server first. And that is going to set things up for us. It's just going to run, it'll run MySQL in a detached container, and it'll cause it to set a student database up. Now the trick here is that we're going to export these variables into our own environment. So we're setting environment variables, and then notice with the -e option down here, we're going to set up environment variables within the container. So we're going to take all this information that we're running MySQL 5.7, the root password is root pw, we're talking about a student user, student password, student database, and the container is going to be called MySQL, and we're going to map port 3306 on the outside to 3306 on the inside. But first we're going to make sure there are no containers running MySQL, and then we'll run it. We'll call it MySQL, we'll pass in all these environment variables, and then we'll set it up and running. So let's take a look at that, how it's going to work. So we'll say clear, and then run server first. And there we go. It's up and running. So we can find that out by saying PS, as we did. It's up and running for 3 seconds now. And then we want to say docker logs MySQL. We want to look at the logs that are being emitted. And that's because we want to make sure it came up correctly, and we'll know that because the MySQL daemon is ready for connections. So that's great. Ready to use it. Now we are going to run another script called run server, The first one is simply to get things set up. So this one is going to stop MySQL. It's going to remove it, so it's stopping the container, removing the container, and then we turn around and run the image again. But this time we're going to do a volume map of that volume we created, and we're going to map it to the internal directory var lib mysql. So that's going to allow us to have an attached volume and separate data state management from the container that's actually running the database. Okay, so let's clear and let's run the server. Takes just a moment. And now let's say docker ps. Yes, it is up and running, so we're in fine shape. Okay, now we want to run a client. So let's take a look at the script that does that function. Cat run client. And this is even more straightforward. We're going to run the same image. Notice it's MySQL 5.7. And this is fairly common to have both the server and client code in one image, because you can obviously make multiple containers from one image. We're just going to have a client container and we're going to have a server container. So we're going to run this. We're going to start the shell, bin bash, and we're going to mount a volume, the present working directory and the subdirectory, which has that data that we looked at. We're going to map that to /data on the inside of the client container. We're going to ask for a TTY terminal, and when it's done, we're going to remove the container, so we don't need to name it. So let's do that. Let's run a client, and now we're inside. And if we go up to data, let's take a look. Those are all the dump files. So this is great. It's looking like we're in really good shape. So what we want to do is leverage things. We want to use MySQL client program to connect to a host 172.17.0.2. That's the internal Docker network address of the other container that's running MySQL as a server. So we're going to say the user is student. We want to prompt for a password, and we're going to connect to student. Okay, the password is student, and we're in. Now we want to let the system do some work. We're going to say source data employees.sql. And that's going to fetch that script and execute it. And that's going to define the database that we want and load the data. So this is going to take a little while. Please be patient. There we are. We've loaded up all the data. Okay, so now we're going to issue some queries to see how we are going to use a relational database. First query that we want to construct is going to fetch the first 10 records from the current employee database department table. And this is a common thing that you're going to do if you're new to a database. You'll want to fetch rows from various tables and just get an idea of what the data is. Kind of explore and find your way around. So we do that by saying select everything, which is asterisk, from, and let me just do it this way because it's a common thing to have the keywords in SQL be capital letters. So we'll say, do it this way. That's the table name, and then we want to limit to 10 rows, and these all end in a semicolon. So there we are. We see what the column names are. So that's the benefit of doing initial queries with an asterisk. You don't know what's in there, and you just want to take a look at the column names and some sample data. So it looks like there's an employee number, there's a department number, from date and to date. And let's take a look and see if there's anything interesting in here. No, it looks like one row per employee per department number. And so that's a kind of a partial view of everything. Okay, well, let's get the first 10 departments. So we will say select asterisk from departments, and we're going to limit that again to 10. And here we've got the department number and the department name. Great, so that looks like a nice little lookup table. Oh, so you might be wondering how you see the tables. Well, you can say show tables. and that's going to issue a query against the metadata structure, and these are the tables that are in the database. So there's 8 tables. All right, let's keep going, and let's take a look at the employee date table. So select everything from, oops, let me type correctly, select everything from department imp latest date limit 10. So that's showing employee number from date to date, and that clearly indicates that they have been in a particular department from a particular day to another day. Now this means they're currently there. It's a special value. You'll see this sometimes in the schemas that there's a terminal value, and notice that this one is an actual value 2000, so it's July 31st 2000. So this is a date range stored in a table. All right, now let's look at department managers. Select everything from department manager, and again limit 10. So we have an employee and a department number from a date to a date. So that's pretty interesting. So we've got the employee number, those must be by implication managers, and it shows the department they're managing. Now notice there's a department here that's repeated. So there's 2 different managers for that department, and notice that there's this to date and there's a from date. So clearly they changed managers on October 1st, 1991. Now let's look at the employee table. Select everything from employees. And that's showing that we've got an employee number, a birth date, a first name, a last name, a gender, and a hire date. All right, now let's look at salaries. Select all from salaries. And here you see the employee number, their salary, and when they were earning that money. So it's also a date range. So you can see the employee number 10001 has 1, 2, 3, 4, 5, 6, 7, 8, 9. No, they go all the way down. They keep getting raises. So nice set of raises for that employee. All right, now let's look at the titles. Select everything from titles. And we can see there's titles such as senior engineer, and there's a date range, staff, senior engineer, and so on. Here we've got a 1005 senior staff, and we've got 1005 staff, so clearly they had a change in titles. Okay, now we're going to move on to the next section. We've explored the data. Now we want to answer some business question. Here's the first one. Who is the oldest employee and what is their age? So let's try typing in this one. This is going to be select first name, comma, last name, comma, timestamp diff. Let's see, year, birth, date, cur date, that's today, right now, as, no comma there, as age from employees. We want to order by birth, date, descending, limit 1. So we're going to use the ordering to get these guys all lined up, and we're going to just look at 1 because we want to know who is the oldest employee. Now let's see how this works. And there it is, Mario Cochran, age 51. Okay, so the next question is going to be, which department has the most employees? So instead of typing this all in, I'm going to do a copy paste here and then just work you through the query. So the copy doesn't have the capitalization. And I did this on purpose so you can see it's a little harder to read when you don't consistently have the capital letters. So select, as, from, and so on. But it's still syntactically correct and the same. So let's see which department has the most employees. And we've got department number 5 with 61,386 employees. Okay, third business question. Which employee has the highest salary and how much is it? So let's type this one in and we'll kind of walk through it. We're going to do a join, so we need to say a T1 table and the first name, and the T1 table the last name, and the T2 table the salary from employees as T1. So we're going to rename employees as T1, so it's an alias or a shorthand. And we're going to inner join that with the salaries table as T2 on, and here's the join condition, on T1 imp number equals T2 imp number. So that specifies to MySQL how to consider joining these tables together. What values must be equal for it to make an association between the rows. And so there's order by salary, descending, limit 1. That takes a little bit longer to do the join. That's a bit of processing. And here it comes back. So it's Mr. Pesh and a salary of $158,220. And the last question, I'm going to leave up to you. See if you can figure this out if you're replicating these labs. The question is, which employee manages the smallest department and how many employees are in that department? See if you can answer that for yourself. So you've got some hints because of the queries that we've already done. Okay, so now we're going to quit. We type in quit. That's a MySQL command, and that takes us out of the client. We'll exit the container, and now we're going to do a cleanup. So there's a cleanup script, and we'll take a look at this. So we're going to remove the Docker image MySQL, and we're going to remove all of the remaining containers that might be there. We're going to remove images, and then the final one, we're going to remove volumes. So we're going to scrub everything. Okay, so cleanup. It's done. Great, so that's the end of Lesson 3, Lab number 1.
Docker data volumes is the next session. We've actually done this before. We've actually used Docker data volumes already. This is going to show you what is possible and go into a little bit more detail about how these things work. A Docker volume is not part of the Union file system. It's just a mount point, basically, on the writable layer that is created inside the container. So it means that a data volume can be shared or reused, so different containers can use the same volumes at the same time if necessary. You can write the data volumes. If you commit the image of the container, it doesn't write the data volume. It doesn't become part of the image. The data volume is something separate. But the most important thing, of course, is that if you delete a container, all changes made to the writable layer of the container are lost unless you've committed it. But if you've got a data volume, then anything that's written to the data volume, it persists as long as the data volume exists. So data volumes, there's actually really two types of them. There's the explicitly created ones, and also you can use directories within the host system to become a data volume effectively. So what we do is we create a volume using the Docker volume create and give it a name. By default, if you don't give it a name, it gets a rather exotic ID and maybe a rather comical name created for it. And you can actually create a volume by specifying it on the run line as well. So you create any number of data volumes, mount it in a container, and add the ---- volume or -v option to mount the volume to a particular mount point. In this case here, we've created the my data and we're mounting it as /opt/data. The path to /opt/data doesn't need to exist, it will get created. In fact, it can exist as well if you want it to. So this is always used for things like the database or any kind of repository that needs to have persistent storage. You'd always use a volume rather than using the storage on the actual container itself. If you do Docker inspect on a container, it'll show you what the mount points are. So it produces a very long JSON string, and one of those entries is the mounts, which shows the name of the volume, which is a very long string, and where it is, which is stored. This is actually stored within the Docker area. It's on the disk, and where it's mounted to, and the mode of operation. So you can manage the volumes, you can list them, you can delete them. If you're going to have some storage that you want to persist outside the life cycle of the container, yes, you'd have to create it, or alternatively use a directory structure within the computer that the Docker is actually running on. So you can create them, you can give them a name, you can list them, and then you can use them and mount them in there. So it's just, so the form is minus volume, or minus v or minus volume, volume name colon local directory on the container itself. So when the container fires up, it'll be mounted to the read-only, to the writable layer on top of the stack of the Union FS. Now, there's a number of different data volumes. You have plugins which decide what they're going to be. There's the actual documentation is rather poor, actually, and because these volumes have options when you create them, and it's sometimes very hard to find out what those options actually are. So examples, there's the GCE Docker plugin, which enables you to connect to Google Cloud persistent disks. So you create a disk within the Google Cloud environment, and then you can use the GCE Docker plugin to mount that disk into your container. There's the Flocker plugin, which provides volumes which are portable across systems as a local persist, which enables volumes to be stored somewhere, anywhere on the host. There's a number of them there, and there's also the default one, which is used. The command run -it -rm volumes -from CentOS /bin/bash. This command will take all the mount points from the existing container, which is CentOS, and copy them. This command starts a new container from a CentOS image. It assumes an existing container called CentOS from which you want to copy the mount points. So what happens is the volumes from option takes all the mounted volumes from the existing running container and mounts them also on the new container. So this enables you to take an existing container with volumes and mount all the volumes as well on the new container, which is a good way of getting the same data on both containers. You can also mount data volumes from a private cloud. This requires installing certain plugins which are associated with the actual cloud environment you're using. And so, for example, Docker has a Google plugin which enables you to access volumes on a Google Cloud environment. So the alternative is to mount directories and files from the host file system. And what you do is you just specify the local path name, and then the container path, and it will automatically mount the local path into a directory which is on the container. The paths must be absolute relative to the root of the file system, and on Windows you use /c/d for the various drives that you might have on it. Don't use an editor on explicitly mounted volumes. What they try to do is, if you mount a file, the editor might try and change the inode of the file when it saves it, and that will cause problems. And so I would never actually mount a file explicitly unless it was something for a configuration or something like that. It's better to mount the directory if you're going to do any editing on it. Edit the file before you mount it, basically. Yeah, files mounted explicitly would probably be read-only. We've got various options that can be specified as well with the second colon. So we've got like read-only and read-write, RO and RW. There are a number of other ones available, which are, if you want to use those, most of them are not very commonly used. Now, interesting thing is, because we've got a union file system, if the directory, which is the mount point, exists and has files in it, then there basically does a merge, and they get copied into the volume. So the files in the container get copied onto the volume if they don't already exist. And unless you specify a no copy option, then it doesn't do that. When you're creating images, this Docker file has a volume command which specifies mount points, and if any content is in those mount points, they will get copied into the volume when you start the container up. So that's just showing you how that works. So you put the stuff in the file, when you do run the command, it will actually populate the data volume. Now that we have introduced the concept of persistent Docker data volumes, Randy will demonstrate how to use them.
Welcome to DevOps Lesson 3, Lab Exercise Number 2, Docker Volumes. Let's go back to our terminal. The first thing we'll do is create a volume that we'll use in this exercise. Docker volume create, name is going to be my data. Now we want to bring down a lightweight distribution. We're going to use Alpine. Docker pull Alpine. And this is tiny. I mean, let's look at this thing. It's 3.9 megabytes in size. It's really a nice Linux distribution. All right, let's run with a terminal interface. And we're going to name the container client. We're going to do a mapping from the outside of my data, which is the volume that we just created, to MNT, mount. We'll run the Alpine distribution and bin sh, which is the Alpine shell. We'll go up into the mount directory. Let's take a look. There's nothing there. Now we're going to do a touch, which creates a file. They're going to be empty, but the main point is that the files exist. We'll call it foo.txt, and we'll touch bar.txt. Look again, they're there, and we can see that they're zero bytes in them, so they're empty files. Okay, let's exit that container. Now we're going to verify that the container is stopped. So we're going to say process status A, let's take a look at it, and it's been exited. Now we're going to delete this because what we want to show you is we've created the state in the other volume and it has nothing to do with this Docker container. So Docker PSA, there are no containers existing. Now let's run, and this time we don't care about preserving the client. We're just going to say remove when you're done. We want a terminal interface. And once again, we're going to map the volume my data to MNT. And we're going to run the shell. We're up and running. CD into MNT, and we list, and there they are. Let's do this way. You can see that they have no data. Then we'll exit, and let's take a look at the volumes. Of course, there it is, a local driver with my data. So that's a demonstration of how to create a separate volume, mount it into a running client, add information to it, change its state, and then verify that it is in fact independent and it can be connected to a different client. That's the end of DevOps Lesson 3, Lab Exercise Number 2.
If we want to now look at the other spectrum, we've looked at relational databases. We now want to look at the other solutions like NoSQL and big data, which are becoming very much popular these days. NoSQL, not only SQL, it's quite an old term. The idea has been that these kind of databases have been around for, say, 50 years or so. But the term NoSQL was coined in the late 1990s, but the actual technologies have existed for quite a long time. So basically, we've got the relational database, which is what we're all very familiar with, but we don't have to store data in a relational database. There are other ways of doing it, and some data really doesn't lend itself to going into a relational database, which is what this is all about. Big data with our friendly elephant Hadoop there. So dealing with the storage and processing of data which has got various characteristics which really don't lend it to going in a relational database. So one thing is high volume. There's a lot of data coming in very quickly. Relational databases don't tend to work too well in that environment. And also the volumes are much bigger, so a typical relational database will go to the order of gigabytes, although it is possible to go larger than that. But we're talking volume in the tera and petabytes, really huge volumes. There's also constantly updating, continuous processing, high velocity it's called, it's constantly changing. And then there's sort of things that are very high variety, which is where you've got different types of data, like you've got text, you've got videos, you've got images. You don't really want to put those into relational databases, as they tend to be, particularly images and videos, tend to be enormous, and they take up a lot of space, and you wouldn't really want to put them in a normal database. So, what's the value of this? Well, we've got the idea is we can get data from different places, different divisions, external sources, and bring it all together. It can improve the quality of it, like cut processing time, make it more transparent rather than having to deal with things that take very long time. A very large database, queries on a database can take quite a long time, like an order of hours. Try different things out. What's in the data? What value can we extract from this data? Separate customers into different demographics so that you can customize your approach to them. Automation, of course. Try new things out. We saw earlier, by analysing the data, you might be able to open new business opportunities. This is one way of doing it, to basically get your business better, more functional, new customers, more volume, and detect problems. So you can also do stress tests as well. So what if analysis, which is very useful, potential scenarios. So basically we've got three types of data in three broad categories. We've got structured data, which is what the relational databases use. They're highly structured. You have a schema consisting of tables and columns and the relationship between tables. That gives you a structure which you can then apply queries to using things like SQL. Then we've got unstructured data, which is no schema associated with it, text, email, social media, instant messaging, that kind of thing, where there's no actual formal structure. And then we've got the semi-structured, which is you've got something like log files. They've all got the same format. Each record has got the similar format. You've got JSON documents, which are very, very popular these days. JSON seems to be taking over from XML, which people don't like too much. It's easier to deal with. And so big data typically works with the unstructured and semi-structured. Although there are some aspects of big data do work on some more structured data than those as well. The comparisons between the two, the size, we can talk about these very large numbers, the petabytes and all the bigger ones still. In SQL databases tend to be on one machine, which you can scale buying more hardware, which is a typical way of improving performance issues, buy more memory, buy more CPUs, more storage. But big data tends to work on smaller machines, and you just keep adding more machines to the cluster to get more scale and more size and processing. Databases work on structured data. Big data doesn't require that. Different types of querying. SQL databases obviously use the SQL language or various flavors of it. The other big data uses different tools depending on how you want to do it. Some are very, very simplistic, doing sort of things like MapReduce. Others kind of try to enforce an SQL-like language on top of the data itself for the querying. Big data tends to be mainly read operations, whereas SQL databases are typically online transaction processing, different there. And the idea is that the SQL databases, the schema is well defined, whereas the processing of big data can take any form depending on what you're trying to achieve. So how does it work? Typically the technologies follow this. You've got high volume, low cost data storage, which is typically lots of machines with their own hardware on it, with their own storage on it. Then you've got the scalable computing, we're basically distributed across numerous machines, so that makes it scale. Notice it's all low cost. And then you've got the analytics, which do the actual work. So it gives you a low cost solution to a big problem, literally a big problem. Big data solutions, what kind of data? Well, you can use database data, transactional data, you can use logs, social, anything, any form of data can be dealt with the big data solution. And but the thing is, you need new solutions to technologies of storage to solve some of the issues. It's seen that like 80% of the world's data is unstructured or semi-structured, so it's often not used, and it's often difficult to process. Scalable computing, I mean by that is that if you double your data size or capacity, you can double your processing capabilities. So it means increasing your computing power operations to make it deal with more data. That's the idea. It's scalable just means adding more capacity to it. MapReduce will come to in a moment. The idea is that computer power is cheap. It hasn't always been that the way. That used to be that hardware, particularly memory, used to be very expensive. So now what we can do is a standard computer is a cheap solution which we can just keep adding networks of the computers together to increase the capacity, just to keep adding more machines to the environment to scale it. So if we've got all this network capacity, then we can have distributed algorithms which enable us to process things in pieces on different computers. There's different challenges. You need a different approach. So you've got batch processing for some real-time processing, are different ways of processing data. We need a different solution to deal with that. So there are many solutions. We just need to take the business problem and find a solution which works for that particular domain issue. Where does it come from? Well, Hadoop and associated technology started out with Google having a problem. If you think about it, Google is indexing the web, which we know there's about 4.7 billion pages of information there. And you've got to be able to search for phrases across those 4.7 billion index pages. That's a lot. So, can we structure the data? Well, we won't be able to. It wouldn't fit in a relational database. Just think about what's required to index the web. You're going to have keys which are all the phrases and keywords and things that you'll want to search on. And then you have the values with the actual URLs for the pages. It's going to be colossal. I mean, how many word combinations would the Google site process in a day? And you've noticed that if you run a query on Google, it happens pretty quick. Do a Google search. If you ask for something really unusual, it might take a while. But if you ask for something fairly standard that people are likely to ask quite a bit, it'll be very, very fast because of various caching things that happen. So can we parallelize the operation? Well, yes. You could petition all the web pages and search each petition in parallel. I mean, it's going to be quite a few petitions. It's the same idea as with the database petitions, but we just break the data into chunks and then do the operation on each one. But then what we've got to do is combine the results at the end of the day. And basically, it's not a unique problem because many of these problems have been solved over and over again into different types of things. In fact, Google themselves had solved this problem several times over the course of their operation. And if you make something custom, it's hard to maintain, whereas if we have a generic solution, that is much better. The idea is that what's the problems they had to solve? We've got very large amounts of data. It's unstructured or semi-structured. We can split it into smaller jobs, but some processing needs to be done locally if we want to do local processing. How do we split up the job into smaller pieces and then bring it back together again? It doesn't want to do it on the same machine. So the idea is to store data on computer nodes, and they developed a thing called the Google File System, which is basically a specialized file system which is highly distributed. So you can store bits of data on a number of different computers in this what looks like a transparent single file system. Data gets moved around. Typically what you do is you take the data, put it into the special file system, which then spreads it around, and then you can perform operations in parallel on each of the pieces which are stored on separate machines. So the operation that is performed is called MapReduce, which I mentioned earlier. So what you do is you take your input data, break it into pieces, and then in parallel you do a processing operation on each of the pieces to produce a result. Then what you do is get the results from all the different map operations, combine them together into the result, which is the reduce step. The terminology MapReduce was developed to describe this operation, and Google basically produced a couple of research papers which describe the file system and the MapReduce operation. And the two documents were basically taken into the open source world and produced Hadoop. Hadoop is the kind of open source re-implementation of what Google described in their papers. So it's a recreation of it. Typically, a lot of big data operations work on key-value pairs. And in fact, unstructured data is often stored in that way. You have a key, usually some string that describes what the object is, a value, which is whatever it might be, whether it's text or an image or whatever it happens to be. And so what happens is that take the input data, copy it into the specialized file system, it's split into pieces. Each piece is given to a mapper. A mapper runs on each of several machines. The mapper splits its input up and creates a key-value pair. So let's think about an operation here where we're, say, trying to count the number of words in a very big document. What we do, break the document into pieces, provide a mapper, and each mapper looks for each word and produces a set of key value pairs. And what you normally do is produce, in the case of a word count operation, you'll take the key will be the word and you'll give it a count of 1. Because you don't want to do any actual aggregation in the mapper, you just want to split everything into pieces. So what you end up with, each mapper has a whole bag of key value pairs where the key is the word and the value is 1. Then what we need to do, get the reducer to add them up. So what happens is the outputs of the different mappers are sorted. All of the ones with the same key are combined together, so what the reducer sees is basically a map, a key value pair where the key is the word, but the value is a list of all of the ones that were generated by all the different mappers for the same word. And then the reducer simply adds all the values together and produces a key value pair, which is the key is the actual word and the value is the actual total count. So that's the process of MapReduce. We've got the Hadoop distributed file system, which is based on that file system that Google designed, which I mentioned earlier. And so what it does is it stores data in chunks. You actually create a Hadoop HDFS file system on your nodes, and then when the data is, you copy your data into HDFS, which then distributes it across the different nodes in your cluster of machines. So if you think about the analogy of a file, if you think how the file system works on a computer, a hard drive is broken up into sectors which are 256 bytes long. The file system will store files in chunks, which may be a number of these sectors, maybe 4 sectors to give a 1K block. And then when you have the file itself, the file is actually spread out over a number of different places over the disk. But the operating system takes care of all that and simply makes it look like the file is one piece, when in fact it's a highly fragmented system, it's spread all over the place. So HDFS takes that to a little bit more of an extreme, where it deliberately fragments the file system and spreads the file around. So the map task run in parallel and processes the data and produce the intermediate results. Then the reduce tasks produce final results from the intermediate results. The reducers may be distributed themselves, so there might be several of them, but you have to make sure reducer sees all of the values associated with the particular key produced by the mapper. But you can easily do that, and there's also an intermediate step you can do by which you can do a kind of in-memory reduce operation after the mapper step to save on some of the network traffic which would normally be required. MapReduce in HDFS. Each of your devices, each of your computers has an HDFS file system and a map program. Then what we do then is we have to copy the input files into the HDFS environment from the local file system. You can only do the operations on files which are stored in HDFS. So the MapReduce operation is run, and the MapReduce operation is, in the case of Hadoop, it's all written in Java, and the mapper can either be a Java class implementation, or alternatively, it can be a set of Unix commands. Because there's a plugin for the operation which effectively creates a mapper from a set of Unix commands. Once the operation is started, the data is split across the processing nodes. The mappers to generate the key value pairs, and then the output of the mapper may go straight into which is run in memory, basically to reduce the amount of traffic over the network. So that's often that intermediate step. It is actually a real reducer you use for the intermediate step, but it runs in memory and aggregates the data for each mapper, and then the resulting data is then aggregated properly when it does the sort and splitting it to the different reducers. So it can be fairly complex, and what happens is then the result is produced by the reducer and it is stored in the Hadoop file system, the HDFS. There is a quirk of HDFS which I find a little bit annoying sometimes. When the MapReduce operation runs, it produces an output directory and it puts the results in the output directory. It's actually in part, so you get part and then something like 5 zeros and part 4 zeros 1 in the output directory. You have to manually delete the output directory before you can run the operation again, because it will not run if the output directory exists, which is a quirk of Hadoop. MapReduce processing is highly distributed. You call it a cluster typically, which can be in the cloud or it can be on a series of network machines. And the idea is that it's highly distributed to get the true parallel processing capabilities that are required to process large amounts of data. Now, there's a name node which is kind of orchestrates the whole process, and one machine basically controls everything, and the other ones do the processing. The data nodes do the processing. Although it is possible to run the name node and the data nodes on the same machine, but the data nodes run the actual MapReduce operations. Now, one thing you have to set up, the name node needs to be able to talk to the data nodes, and it requires passwordless SSH communication. That means that you need to generate SSH keys on all the data nodes and copy the public key of each data node onto the name node so that it can access via SSH without specifying a password. And when you run the SSH key generation, you mustn't specify a passphrase to lock the private key, otherwise that'll require a password which defeats the object. And there may be security implications here, but typically the nodes all run on a trusted environment of some kind. You might have heard of the Hadoop ecosystem. Hadoop is now under the umbrella of Apache. The Apache Foundation started out pretty much as the Apache web server and has seemed to have encompassed all things web and many other things, including big data. And Hadoop is Apache Hadoop, and it's basically HDFS file system and the MapReduce. The actual MapReduce, the Hadoop has got an API which is written in Java, which enables you to create mappers and reducers as Java programs, or use pre-existing Java implementations which enable the mappers and reducers to be things like Unix commands. Now, HDFS and MapReduce are fairly low level, and people say that they really don't want to work at that level because it's too detailed, and finding the MapReduce operations is quite an ordeal, quite a task really to decide what they are, and it's a fairly low level API. So what happened is an ecosystem has developed around it. So all of these things, basically extensions to Hadoop, many of them actually require Hadoop to work, and they sit on top of Hadoop to provide extra functionality and get rid of the need to work at the very low level of MapReduce. So virtualization enables organizations to provision and maintain different computing environments. The environments are stored centrally so that you don't have to update individual machines. Certain Linux kernel enhancements such as control groups facilitate the implementation of container virtualization. Docker is a powerful tool that simplifies the creation of images and containers from base images. Docker images are constructed by adding layers to a base image. Registries manage repositories of images. A repository contains different versions of the same image. Docker Machine allows Docker to be installed and managed on remote machines. That's the end of the session today. Thank you very much